let Pn be the population density of fish in some lake, say, at the beginning of year N, not the number of fish, but the population density of fish. What would that mean? Well, I'm trying to make it as a fraction of an assumed maximum sustainable population. So you would have some hypothesized maximum sustainable population. You might be wrong in your hypothesis, but you have some hypothesis. I think, for example, White Bear Lake, which is a fairly big lake for the cities, can hold, I don't know, 10 million bass. Is that too many? I don't know. It's a fairly big lake. And so if somehow you're able to measure the number of bass at the beginning of year N to be 5 million, then you wouldn't literally count them, by the way. You'd have to have some other method for doing it. This ratio would be 5 million divided by 10 million, which would be 0.5. You're at 50% of the sustainable population. We're going to let delta sub Pn be P sub n minus P sub n1 minus 1. Maybe you want to write down just some of these equations if you do want to write down anything. What is that representing? Well, just like in calculus, capital delta represents change in. So effectively, this represents the change in P. You might say, from time n minus 1 to time n, the subscript of n here emphasizes it's from time n minus 1 to time n. If you think about that, the first delta P you would have then would be delta P1. That would be P1 minus P0. And then delta P2 would be P2 minus P1. What we're trying to do here is we're trying to come up with an equation that's going to relate what's called the relative rate of change of Pn in a discrete sense, not a continuous sense, not like calculus, to the population density itself. That's what we're after here. This ratio does represent the relative change in the fish population density during year N. If it's helpful, think about an example here. I'll try to show both the Mathematica and my writing at the same time. Think about an example here. You know, if P0 is, for example, 0.5 and P1 is 0.6, that implies delta P1 minus P0 is 0.6 minus 0.5 is 0.1. And that would imply the relative change in the density, which you could call, yeah, I probably should have called it a relative rate of change. Maybe I'll go ahead and make that change. Relative rate of change. It's a discrete rate of change. Would be delta P1 over P sub 0. 0.1 divided by 0.5, which is 0.2, which you would commonly write as a percent. That would be 20%. The population grew by 20% from time 0 to time 1 is the idea there. Let's go ahead and call that a relative rate of change. It's a discrete rate of change. It's not a continuous rate of change like in calculus. And a seemingly reasonable model for the growth of the fish might be that this relative rate of change is proportional to 1 minus Pn. For some proportionality constant k, this equation might be true, or at least a good approximation. Why? Why is this indeed reasonable? Well, think about it intuitively. Imagine P0, say, or Pn minus 1 is a very small number, like 0.01 or something. That means the population density of the fish is pretty small. It means the population of fish is small relative to how many fish the lake can hold. Lots of room for growth. This is a growth rate as a percentage. Should be a large percent growth rate if the fish population is small. There's so much room for growth. There's a lot of food. 1 minus P 0.01 is going to be 0.99. a relatively large number compared to the case where Pn minus 1 is close to 1, 0.99 or something. If Pn minus 1 is 0.99, then you're close to the carrying capacity of the environment. 1 minus 0.99 is going to be small, 0.01. And the relative growth rate will be small. You can come up with differential equations that have a similar kind of feel to them as well. But we're looking at a discrete model here. This is sometimes called a difference equation when you have a discrete model. What's the goal with this? The goal is to solve, if you can, for Pn in terms of P0. Can we solve for Pn in terms of P0? That's one goal. I'll call that one goal. That would be solving the difference equation. But we're actually going to not focus on that. In general, that's a hard thing to do. And I think in this example, it's pretty hard to do. Instead, we're going to use iteration. Cobweb plots, we'll go back to cobweb plots. By the way, the plot we made with Newton's method is similar to cobweb plots, but it's definitely not the exact same thing, right? We have the curve crossing the axis. We're looking for the root. You're still making some sort of plot in a weird kind of way, but it's not the exact same thing as the cobweb plots from last week, where we also wanted to have the line y equals x in there, right? Well, here we're iterating a function. We're not talking about finding a root. So we don't want to use Newton's plot here. We want to use a cobweb plot. So while this was one goal, our main goal is actually different. Essentially, experimentally, this is math experiments. Experimentally, can I spell experimentally? Experimentally is what that's supposed to be. Observe what happens when this function in the Mathematica right there is iterated. Observe what happens under iteration. That's really our main goal. And what we're about to do in embarking on this experiment here is twofold. We're going to reinforce some ideas from last week, and we're going to talk about some new ideas that I hope you'll find pretty interesting. I hope to kind of blow your mind. Not literally, but you know, that you'll say, hey, that's pretty amazing. And to educate you about, well, weird things can happen when you're doing these kinds of schemes of numerical analysis. You should be aware of these weird things. And it's a cultural thing too. This is actually relatively famous. In fact, this is going to be associated with a famous constant that you probably never heard of before, but it is relatively famous. And we'll talk about that constant. It's called Feigenbaum's constant. So first thing to do is take this equation and figure out what function we want to iterate. We don't have Pn isolated on one side. Well, that's relatively easy to do. Do some algebra. Multiply both sides by Pn minus 1, and then add Pn minus 1. That's what's done here. See the relationship there? I multiplied both sides by Pn minus 1, and then I added Pn minus 1. That's actually now a quadratic function of Pn minus 1. If you group together, if you expand and group together the terms that involve Pn minus 1, double check in your mind that it expands to this. So in other words, we're iterating this function. I'm calling it f sub k. Maybe I should have called it g sub k, since these functions that we iterate, we typically call g, but it's okay. That's the function we want to iterate. That's kind of similar to the example we did last week with the mu. Remember that logistic example? It's not too different. The logistic model from last week the logistic functions say, I don't remember if I used an F or a G. It was F sub mu of X equals mu X times 1 minus X, mu X minus mu X squared. This is kind of a similar function, a very similar function, in fact, but definitely not exactly the same. The parameter K is not playing the exact same role that mu did. The fixed points of this example from last week, if we set this equal to X and solve for X, we did this calculation last week. We got this, and the fixed points, FPs, stands for fixed points, were X equals 0 and X equals, what would it be, mu minus 1 over mu? That's what we got last week with the logistic model. With this new example, the fixed points are not quite the same. Well, one of them is the same. 0 is still the same. New example, F sub K of X equals 1 plus K times X minus KX squared. Set that equal to X to find the fixed points. We want to rearrange, subtract X from both sides. We'll get KX minus KX squared. Now we can actually factor out not just an X, but also a K. And the fixed points, this is kind of nice. They don't depend on K. They're 0 and 1. They're independent of K. That's kind of nice. The second fixed point here doesn't depend on the parameter like this one did. The second fixed point is always 1, no matter what K is. What else did we observe with the example last week? We observed sometimes that the iterates approached the fixed point, sometimes they didn't. And it was dependent on the derivative at the fixed point. Let's go ahead and confirm the calculation here. With this logistic function example from last week, what's its derivative? F sub mu prime of X, taking the derivative of this, actually this thing here, sorry, almost made a mistake, is mu minus 2 mu X. If I plug in this second fixed point here into that, and simplify, when I replace X with mu minus 1 over mu, the mu's will cancel there. Looks like I'm going to get that. If I didn't make a mistake, double check to make sure I don't make a mistake here. Looks like this simplifies to 2 minus mu. And that's going to be an expression. What was the key condition? We wanted, if the slope of the graph at the fixed point was close to 0, then it was a stable attracting fixed point. You remember that? Close to 0, between -1 and 1, technically. That's going to happen when mu is between 1 and 3, right? If mu is 1, this equals 1. If mu is 3, it equals -1. Once mu gets bigger than 3, we saw that the fixed point was no longer attracting, was repelling, unstable. Attracting means stable, repelling means unstable. Effectively, something called a bifurcation occurs. Talk more about that later. Now, something similar happened with this example, focused on the fixed point at 1. What's fk prime of X using this formula? It'll be 1 plus k minus 2kx. Plug in 1 into that, and it'll simplify to 1 minus k. That'll be between -1 and 1 when k is between 0 and 2. Right? If k is 0, that's 1. If k goes up to 2, it becomes -1. Once k gets bigger than 2, seems like the nature of this fixed point is probably going to change. Let's now observe and see if that happens. We are going to use the cobweb plot code now. I also have a cobweb plot code with no data, so I don't see any numbers. If I'm going to use that, it runs faster. By the way, we can confirm with Mathematica's solve command that the two fixed points are 0 and 1. We can confirm their derivatives at 0 and 1 are 1 plus k and 1 minus k. We just did this calculation of 1 minus k a minute ago. All right, what happens when k is 0.7? Remember, the key thing is, the interesting thing is probably going to be k is 2. But what happens when k is 0.7? Remember, we are still talking about the model, the fish, right? So we're trying to think about the populations here. I'm going to use NestList here initially. K is 0.7. There's your initial fish population density, 0.1. If the carrying capacity of the lake is 10 million, this represents 1 million fish. Doing 20 iterations, wow, how about that? What a natural thing to happen. The fish population is heading toward the carrying capacity of 1. It looks like 1 is an attracting or stable fixed point here. Can that be seen graphically? Yep. There's a cobweb plot. So we started at 0.1. We go up to the curve, over to y equals x, up to the curve, over to y equals x. Here it's looking like a staircase, forcing us visually to head toward this fixed point at 1. Would we still head to that fixed point if we used a different initial condition like 1.1? So now that's over the carrying capacity. You got too many fish in the lake. Yeah, it's now heading down toward 1. 1 is stable from both sides. And by the way, this kind of stuff is something you're going to do on your homework assignment as well. You're going to be experimenting with the cobweb plot and, again, giving some brief explanations of what you observe. We can make an animation for fun of the staircase here, heading up toward that fixed point as we continue iterating. What about k is 1.9? So this is close to 2. We're heading toward 1, but now it's oscillating. It's no longer a monotone sequence. It's oscillating. I mean, it's monotone and increasing at first. So now when k, this constant of proportionality in that difference equation, is larger, 1.9, the fish population grows at first, but it overshoots the value of 1. The density goes above 1. The actual population goes above the carrying capacity. Now, again, keep in mind in real life, you may not really know the true carrying capacity of the lake. So, this is all hypothetical. But if it did overshoot it, in the next iteration, a lot of fish die off because there's not enough food, you might say. And so the density goes below 1. Then it goes back above 1. And you're oscillating back and forth around 1, but we're still in the end converging toward 1. What happens with the cobweb plot? Isn't that fun? It starts spiraling. You can see it like this. Staircase at first, but then we spiral. It's still stable. It's still an attracting fixed point, though. The derivative there is now negative. But it's not too steep. With the other example, was it positive? Yeah, it was a slightly positive derivative there. So maybe with a positive derivative that's close to 0, you monotonically increase or decrease toward the fixed point. And maybe with a negative derivative that's not too far from 0, you spiral into the fixed point. Yeah, the derivative is getting close to -1 now. All right, let's go above k equals 2. Let's go to k equals 2.1. So it starts out similar. We start out, once again, increasing and shooting above 1, so we shoot back below. But in the long run, it's not approaching 1. So it's different in the long run. 1 is no longer, the fixed point 1 is no longer stable. If I copy and paste this, change the 1.9 to a 2.1, the derivative is negative 1.1. Steep enough that the fixed point is no longer attracting, it's repelling. And so my initial condition here was a small one, 0.1. What happens if I start really close to 1? It does go away from 1. It truly is repelling. And that'll happen even if I start really close to 1, but not equal to 1. But you might need to go more iterations to see it more. Yeah, those iterations are going away from 1. Can you still describe the behavior of those iterations in the long run? Let's pick 1.1 instead here. There's still a pattern here. In the long run, it seems like we're heading toward bouncing back and forth between 1.12865 and 0.823735, right? There is a long run behavior, it's just not a fixed point. It's called a 2 cycle, a cycle of period 2. That's what it's called. Visually, it's a little hard to see, but we're approaching the cycle of period 2. It might be this inner one, this inner box here. Let's see if that happens if I animate it here. Okay, we're going away from it there. That's a different picture, actually. So now we're approaching a box on the outside when we start close to the fixed point. If we start further away from the fixed point, we approach the same box, so to speak, but now from the outside going in. When you start close to the fixed point, in this case, you're going inside out. Here with this example, we're going outside in. We are approaching a stable 2 cycle. Is there a way to figure out what that 2 cycle is? We'll come back to that. What if K is 2.5? What's going on now? Look at the long run. In the long run here, we're approaching not a 2 cycle, but a 4 cycle. We're going between about 0.536, then 1.58, and 0.701, and 1.225, back to 0.536, 1.158, 0.701, 1.225. We're bouncing back and forth in the long run between 4 numbers, cycling between 4 numbers. Is this a cyclic group? No, no group theory. Has a similar feel, but we're not doing a group operation. We're applying a function and we're going cycling between 4 numbers. Yeah, it's called a 4 cycle. Are there 3 cycles too? Well, if there are, we're not approaching them. Oh, a little too fast there to see very well. I could slow it down, but let's keep going. K is 2.55. Now what's happening? We're approaching an 8 cycle. 0.494, 1.13, 0.752, 1.227, 0.5155, 1.5, 0.705, 1.235, back to 0.494. Start there, you have to go 1, 2, 3, 4, 5, 6, 7, 8 iterations to get back to close to where you started. Now 1.13 and 1.15 are not very far away from each other, but you can see there is a clear distinction between them in the pattern. We're approaching an 8 cycle now. I'm not going to animate it. K is 2.57. You could argue maybe based on comparing, say, this number and counting in between, that we're approaching a 16 cycle. The period keeps doubling. It's called period doubling. A little bit bigger than K, 2.573. Is it a 32 cycle? I think so, but I don't want to count it. There's a 0.485882 there, pretty close to 0.485 there. I think if you count, you'll get 32 iterations to get back to close to where you started. Here's what the picture looks like. K is 3. Is it a 64 cycle? Oh. Chaos! When K is 3. What's chaos? It's where the numbers go all over the place. Well, that's not the official definition. The official definition of chaos and chaotic behavior is difficult to explain in a short amount of time. One big characteristic of it is that it's very sensitive to initial conditions. For example, if we use K equal to 3 and an initial condition of 0.1111, after 100 iterations, we're close to 0.0187. If we change the initial condition slightly from 0.1111 to 0.11111, after 100 iterations, you're at a completely different number, 1.22, instead of 0.0187. These seeds, these initial conditions were 0.00001 apart. 10 to the negative 5. Yet after 100 iterations, if they're a prediction of fish populations, they're completely different. That's called sensitive dependence on initial conditions, and that's one key thing about chaotic behavior. Yeah, the numbers are all over the place. In fact, you could make a histogram showing that the numbers go all over the interval from 0 to 1.5 or so. Is this a probability distribution? Is this random behavior? Careful. It is actually completely deterministic. The initial condition does technically precisely determine all the other values. In fact, if the initial condition is rational, all the other values forever have to be rational. Fractions, now they'd be humongous numerators and denominators. But they are completely determined by the initial condition. However, it behaves in a random way. If you didn't know which step you were at, you could use this essentially as a probability distribution to model where you would guess you'd be at. Here's something interesting. This is a different cobweb plot, a different animation. Let K change. In this animation, I'm going to use the same seed, 0.1 all the time, and see what happens as K changes. When K is 1, we head toward this fixed point. As K increases, oh, this is beautiful. We continue heading to the fixed point. The fixed point's always 1, but it's changing the slope at that point. When we get to K equals 2, the slope becomes -1. We are still approaching it there. It's still attracting. But when K is 2, it changes from attracting to repelling, and a hole opens up in the middle, and we get our box. Once K gets big enough, the box changes from essentially having 4 sides to like having 8 sides or something. And then 16, and then 32. That gets difficult to see. And we get large enough. And it gets wild, and that's why it's called the cobweb plot. There are some values of K where things are less wild. They're called islands of stability. I'm serious. Look it up. Islands of stability. in a sea of chaos. I'm serious. That's the official name. Islands of stability in a sea of chaos. Yeah, when K is 3, that's the most extreme case, you might say. I got a section here, fixed point iteration theorems and proofs. That's not really our main goal there today, so I'm going to skip it to this period doubling route to chaos and bifurcation diagrams. Really, for the really fun stuff? All right. K equals 2 is the first period doubling bifurcation value. Anybody take difficult with linear from me? Okay, yeah, you did. Okay. Remember bifurcations in difficult? Okay, this is kind of similar. What we're thinking about is what happens as K changes. Now, wait a minute. Isn't K a constant? Well, it is for any particular fish population in any particular lake. But if you change the fish and you change the lake, maybe K is different. What are we trying to do here? Remember, the key was what is the slope of the function at that fixed point 1? So what am I doing? I'm solving for when this derivative first equals -1. I already know the answer. K is 2, right? That's just confirming that. K is 2. That's where that first derivative, that slope, first equals -1. Once K is bigger than 2, then it's steeper. It's like -1.1, then -1.2. The slope gets steeper, more negative as K gets bigger. And yeah, you can compare a cobweb plot, for example, when K is 1.95, spiraling in toward the fixed point when the slope is less steep, compared to K when K is 2.1. Now the slope is more steep than -1. The scale doesn't make it look like it necessarily is here, but it is a slope that's more like -1.1 or something, and we have a period 2 point. Turns out the second period doubling bifurcation value, where we change from having a 2 cycle to a 4 cycle, is about 2.44949. How would you find that? I'm defining a new function here, f2 of x, to be f of x. Why am I doing this? I'm composing f with itself. A period 2 point of f should be a fixed point of this new function. Why? f2 of x, maybe subscript of k, is fk of x. Why am I putting the 2 like that? Because, well, it's actually somewhat traditional to make it a superscript here, but that's a little confusing because it makes you think it's a power. If, what should I call it? A, B, etc. is a 2 cycle of f sub k. So A, B represent numbers that are, so when you iterate, you're cycling between the numbers, say exactly. Then F2 sub k of A is going to be F sub k of A, will be F sub k of B, will be A. If iteration of f sub k causes A to go to B and B to go back to A, etc., fk of A will equal B. And then fk of B will equal A. So for this new function, f2 sub k, it's going to have A as a fixed point. It's going to map A to itself. Same thing will happen with B. It'll map B to itself. This new function, formed by composing f with itself, has the 2 cycle as a fixed point. Both numbers in the 2 cycle as fixed points, in fact. It's also still got 0 and 1 as fixed points. What function is this? Well, it's 4th degree. Here it is. Yikes. To find its fixed points, you'd still want to set it equal to 0 and solve for x. Can Mathematica do that? Turns out it can. In part because 2 roots are easy to find. 0 and 1 are easy to find. What does this look like graphically? Let me change where this is here. What does this look like graphically? Excuse me. So the red curve is f. The blue curve is f composed with itself. As k increases, you can see they both, for small k, have fixed points at 0 and 1. But when k is large enough, like 2, watch what happens. The blue curve, which is 4th degree, starts looking more like a 4th degree does. And once you reach k equal to 2, this blue curve is starting to fold enough, you might say, that it ends up crossing y equals x now 4 times when you're past 2. We've gone from having 2 fixed points from both of them when k is just less than 2 to now having 4 fixed points for the blue one. These two here, watch where my cursor is, and here correspond to the period 2 point of the red graph, f. As k continues to increase, they get further and further apart, but you still have those 4 points. Where does the next bifurcation occur? When the derivative of f2 at, say, the bigger period 2 point of f equals -1. Actually, that's where the previous one happens. Where does the next one occur? At about 2.54409. We can create yet another new function, f4, to be f2 composed with itself. If f2 is 4th degree, what degree does f4 have? Yeah, 16th degree. It's a 16th degree polynomial. What are its fixed points? I don't think I want to find them. What happens if we graph it? Now remember, this new bifurcation, this new change that occurs in the number of fixed points, doubling of the number of fixed points, bifurcation, the number doubles. About 2.544, let's see if that seems to happen here now. 2.544, keep that in mind, 2.544. So we have the first one. The pink graph is F4, by the way. It looks almost horizontal there in the middle. As k approaches 2, so we have the red one is the original, the blue is the 4th degree, the pink one's the 16th degree. When we reach k equals 2, the pink and the blue both now have 4 roots once we go past k equals 2. Again, we're after k equals 2.544 here for the next bifurcation value. The pink one starts oscillating more than the blue one now. And once reached k equals 2.544, or maybe smaller, excuse me, 2.449. 2.449, yeah, we're already past it. Look up here, for example. The pink one is starting to fold enough that now we're going to get more fixed points of it. That's for F4 now. These are period 4 points of the original function. Yeah, I'm saying things a little wrong here in spots, but you're getting the basic idea. Can I figure out at least one root of the 4th iteration, the F4, which represents, whose fixed points are period 4 points. I'm going to use find root to find the biggest one here and think of it as a function of k. And I'm going to plot this function of k. Question?
It's supposed to cross 8 times, right? Because if you have 4 and then...
I think I was not quite to the period 8 yet. We were still talking about the period 4. The next bifurcation to period 8.
The pink one should have been 8, right? It crosses 8 times because if it was 4 for the blue, then pink would cross 8 if it doubled.
Yeah. I'm trying to plot the biggest one here as a function of k. So the horizontal axis here is supposed to be k. It's actually not doing a perfect job probably because of chaotic behavior. This is supposed to be k, and this is supposed to be the biggest fixed point of f, or the biggest fixed point of f4. 1 for a while until you get to k equals 2. Then it becomes a large one here until you get to k equals 2.449 or whatever it was. Then it's here, and then it behaves chaotically. In a smaller window, it would look more ordinary. We're running low on time. More bifurcations occur to period 8 cycle, period 16, period 32, period 64, etc. It keeps doubling. And the k values where these occur keep getting closer and closer together. It's happening faster and faster as k increases. If you compute these successive ratios that you see there, it approaches something called the first Feigenbaum constant, which is about 4.6692. Here's Mathematica's computations of those things. And this is an example of a universal constant like pi or e that you've never heard about before. Why haven't people heard about it as much? Well, because it's harder to explain, that's why. But why is it called a universal constant? Because it's a constant that shows up for many, many examples like this. The way these period doubling bifurcations on the route to chaos happen is the same, essentially for infinitely many examples. And you get the exact same constant that these ratios are approaching. I tried getting Mathematica to make a bifurcation diagram, a full bifurcation diagram of this. It's computationally intensive. Here's the picture I got. A better diagram made with probably a better program for doing this kind of thing looks like this. So again, what are we seeing here? And this will be the last thing I emphasize today. What are we seeing here? Why is it not getting smaller? It's getting bigger as I lower the magnification. What in the world? We're seeing, I'll explain this again next time. We're seeing, again, the k-axis horizontal. And this is effectively the x-axis here. When k is small, we're seeing, okay, it's not this particular, it's not our example. Sorry. This is the logistic map example, mu. When mu is bigger than, if mu were less than 3, we'd see only one curve representing one fixed point that's bigger than 0. And then a change, a bifurcation, a forking. Forcation means fork. A fork into 2 pieces occurs, and you have 2 period 2 points. And then you have another bifurcation occurs, you have 4 period 4 points, and then 8 period 8 points, etc. And effectively, by the time you reach where everything looks real solid, you have reached chaos. Though it's not chaos that fills up the entire screen in the cobweb plot. And you also have islands of tranquility in a sea of chaos represented by these open regions. That's too much information to handle completely in that amount of time. What do you need to know about this? I'll talk about it next time, but we're out of time for today. The assignment that's due in the Calc 1 project is not quite so heavy duty, okay? You are just experimenting and explaining your observations.
Yeah,